Okay, good afternoon again. So today we'll be taking a little bit different viewpoint than yesterday. Yesterday we talked a lot about MPI, PGAS, but today's focus will be, can we take advantage of all the InfiniBand and new RDMA technology for the big data? Okay, a lot of people have been talking about it, but what is the state of the art and what are the limitations and how we can enhance it? So that's what will be the talk. So as most of us know, these days there is a lot of discussion about the big data in the business analytics area, and the amount of data has been exploding. The rate of information growth appears to be exceeding Moore's law, and people want to process or mine all those data and then try to make sense out of it. So that is the biggest challenge. And then in that community, there are different kinds of parameters or metrics being designed. Like there are 3 V's, like the volume, velocity, and variety, the features in which the data, different data sets come. And in addition, people have also started adding some more features like value and veracity. But it's not just the business analytics. Now the question is from the scientific side. I mean, many of us are here from the HPC side. And as you know, like as we are talking about like multi-petaflop systems, exaflop systems, the amount of data is also exploding. And you take any of these examples like climate modeling, combustion, fusion, astrophysics, bioinformatics, there is a lot of data which comes. So you need to manage the data and also do analysis and also visualization. So if you put them all together, that itself is also a big data problem. And many of us, like all these large supercomputer centers, the task is running in a very data intensive mode. So here we run like large scale simulations on supercomputer centers, dump the data to the parallel storage systems, collect experimental and observational data, and then move experimental or observational data to analysis sites, and then do the visual analytics. So there are a lot of steps in which we process the results which come out of this supercomputer center. Now, in order to process all these things in the area of the big data, of course, there are a lot of different kinds of middleware or the software environments are emerging. The common one is the Hadoop, which we'll be talking today in depth. So this is the most popular framework, and it has a lot of these components. I'll very gradually introduce those things. And also there are a lot of newer softwares that are coming like Spark, Spark, Sturm, S4, and in a different area, like in the enterprise data centers, there also a lot of data is being generated, and to handle that, there is this Web 2.0 environment is coming with Memcached. It is basically a high performance distributed memory object caching system. So today in the talk, I'll try to focus one of this side, like the Hadoop, and then the other one is the Memcached. Now let's focus on the Hadoop. So the question is, who are using Hadoop? So if you take a look at here, I just added some of these logos here. So these are the organizations or companies that are actually using Hadoop in a production environment. Okay, there's a lot of names look familiar here, and they actually use the Hadoop framework to process a lot of day-to-day data, like Facebook. I mean, many of us use Facebook, and actually in the background they're using Hadoop to do a lot of this processing. Now this was like a trend of Hadoop. What has happened over the years, like broadly, if you know, like it started from Yahoo, and it tries to show this, like starting from here, how things are scaling in terms of number of nodes and as well as the amount of data in the file system, which is the HDFS, Hadoop Distributed File System. I'll again introduce soon. So over the years, you will see that the things have scaled up to 42,000 nodes. And in the file system, like 365 petabytes. And then there is a concept of slot hours in terms of the number of cores and how many hours these jobs are running. So it's like 10 million daily slot hours. And in that big data community, there is something called a Jim Gray, the famous researcher. He had a Jim Gray sort record. So over the years, like they have been trying to see how the number of nodes are increasing, and then the raw data is also increasing, and then they run this sort record. So here it is like 1.42 terabytes per minute. That was attained in this around 2012 time frame. So with that kind of a background, this will be like the outline for the talk. I'll go into a little bit of details of Hadoop and Memcached, and then talk a quick look at like trends in networking technologies and protocols. We have seen that in many of the talks. I'll just quickly recap, and then trying to put these things together, trying to say that this HPC world has already moved ahead, and we are talking about like MPI, PGAS, and all in a microsecond latency and up to 100 gigabits per second bandwidth, but the big data is lagging behind, and they are still like trying to use Ethernet, or even they used to come to InfiniBand, they are still using IP over IP. So there is a big gap there. So I'll try to outline these challenges in accelerating Hadoop and Memcached, and then I'll go into some more detailed case studies. In my group, we have been working on this for almost like last 2.5 years, trying to take a lot of knowledge, whatever we did in the MPI side and PGAS side, to the big data side. Okay, and I'll show you some designs through which we can actually accelerate a lot of different components of the Hadoop, HDFS, MapReduce, HBase, RPC, etc. And not only this basic Hadoop, a lot of people are also trying to just run the MapReduce over a HPC system using Lustre. They don't want to use the HDFS and all, just Lustre. The traditional HPC system, if you have, can you actually try to run MapReduce and get more performance out? So I'll try to focus on both these things, and then go into the Memcached, and then I'll try to outline some of the open challenges as a community we need to solve if we really want to push this direction ahead, and then I'll conclude. Okay? Now, how many of you are familiar with Hadoop or Memcached architecture? No? Only few? Okay. So, sounds good. So let's start here. So this is how like the basic Hadoop architecture looks like. So it is an open source environment from Yahoo, and the major components are here. Like this is how the typical Hadoop architecture look. There is a Hadoop distributed file system. So just like HPC, we have parallel system like Lustre, GPFS, and all those things. So here it is a Hadoop distributed file system, and then on top of that, you have, let's say, this is the MapReduce, which is the basic component in which you try to use the MapReduce framework. I'll try to show an example in the next slide. Or you can have also, this is for computation, and you can also have like a database oriented operations like HBase, etc. here. And then on top of that, these are like the components, and then you can have the end user applications. Okay? And then this underlying, there are some different other components, and one of the common component is the RPC, remote procedure call. It is very extensively used in all these components for the components to talk to each other. And originally it was designed to scale as like bigger and bigger data comes, and it was written with Java. Okay, so in one way it is good that it provides a very portable environment, but if some of you are familiar with Java, trying to extract performance is very hard. Okay, and that with high performance networking. It's not like a C program and all, you can very tightly bind to the underlying network, so there are a lot of challenges there. And also what happens in the big data steps, you will see that sometimes there is a lot of high amount of communication takes place, and this is where things get bottleneck. Okay, and the question is, can we accelerate that? Okay, that will be the central theme as we go along. So this is like a typical MapReduce framework. Okay, has everybody heard of like at least MapReduce? I'm sure many of you must have heard. So the idea is that it is a distributed computing model. So let's say you have a lot of data. So what you want to first to do, like on the different nodes, try to create some mappers, so they will work on the local data. Okay, so let's say think of like a big amount of data is there, and I just want to do word count, which is a very simple example, like trying to see how many occurrences of each of these words exist in that file. Okay, or in the document or on the web page or anything. So what I try to do is that take that file. Let's say I have 10 nodes. I divide them into 10 different parts and then give it to each of the nodes. And then I run one mapper or even multiple mappers per node just to analyze the local data. So they can do like a bin counting, say, okay, word X occurs 5 times, word Y occurs 2 times, like this. They can totally do the local computation. So there is no communication involved. So these are called the map phase. And that's what we are seeing, like a word count, you can do a local sort. Okay, and then after this phase is over, now obviously we need to aggregate the results, and this is where like the shuffle happens, and sometimes if it's a big amount of data, you also want to put it to the disks, okay, and then you do the shuffle. So this one is sending its local results to these other nodes, and these are called reducers. So we have a set of mapper process, then we have a set of reducer process. Now the reducer process are taking data from the mappers. So each mapper has to send data to these reducers, and then you finally do the merge, and then you get the end result. Okay? And then once you get the end result, so this is mostly the communication intensive and IO intensive part, and then once you get these results, they also can go back to the HDFS. Okay, because you might be trying to use that data again for some other application or some other components. Okay, and in the HDFS, it is also has been designed in a very fault tolerant manner. I think yesterday we heard in one of the talk, I cannot remember. If you think about HPC, when we are talking about purely on performance, but not much on fault tolerance. But in this framework, the fault tolerance is built in. So that means when the HDFS, every data is actually replicated to multiple nodes, and the default is 3. So typically you try to copy it to one neighbor, then another on the same like the server or the blade, and then another in the rack. So in case anything fails, this the overall framework can actually try to recover and then continue. So the fault tolerance is built in. So that's why this data here we are showing, they also need to be replicated. Okay, so there is an overhead of replication, but the fault tolerance comes automatically with it. Okay. So then if we go into a little bit down, so this is how the HDFS file system looks like. So this is the primary storage for Hadoop. As I said, it's highly reliable and fault tolerant, and this has been adopted by many reputed organizations. So the broad idea here is to have a one name node. It stores the file system namespace. That means what file resides on each of these data nodes where the actual data blocks are stored. And then there is this RPC communication takes place to connect with name node or to communicate with the client. Okay? And as I again said, like these are developed in Java for platform independence and portability, but primarily it uses sockets at its lowest layer. And this is where we see that there is bottleneck in the communication performance. So if we abstract it up with respect to like clusters and networks, this is how you will take a look at the figure. That means we have HDFS clients and we have these HDFS data nodes. And the data nodes again can have hard disks, SSDs, you can have multiple disks, multiple SSDs. And because this like we are talking about file system, what kind of infrastructure you have here actually makes a big impact. We'll see. And not only that, it also has some interplay with high performance networks. I'll show you some results. Then the other component is HBase, like it's just like a database component. This is the Apache Hadoop database. It's a semi-structured database to get scalability. Again, like it's an integral part of many data center applications, like let's say the Facebook, the social inbox is actually implemented here. In terms of the HBase. And here we see like this is an HBase client, then there is an HBase master, then intermediate we have some HBase region servers, and they are interfacing with the HDFS component we talked earlier. Now here what happens if we again abstract it up to understand the interplay, here we'll see that these are the HBase clients communicating with the H region servers over high performance networks, and then the H region servers are communicating with the HDFS data nodes also over the network. So for HBase operations, you go over the network twice. Okay, so we'll see, depending on if we can accelerate the communication parts, we should be able to see even more benefits in the HBase. Any questions so far? Are the things clear? This is afternoon session after good lunch, you know, so everybody has to talk. Okay. At least I'll keep awake myself. Any questions? Okay. So let's take a look at the little bit different one, which is the Memcached architecture. So this comes from the enterprise data centers, like multi-tier data centers. As many of you know, every day we interact with this kind of data centers, whether we are trying to buy an airline ticket, or we're trying to do in the Google query, or trying to buy something from Amazon, or trying to interact with our bank accounts. So all these systems are currently designed in this manner. So that means we have something called the front-end servers, then we have some Memcached servers, and then the database servers. So the actual data actually resides here, and the idea of these Memcached servers, this is like an integral part of the Web 2.0 architecture to have a distributed caching layer. Okay? So what it does, it allows to aggregate spare memory from multiple nodes, and it can be used as a general purpose manner. So let's say I have some 16 nodes here, and if I take 2 gigabytes of memory from each node, I have a 32 gigabytes of distributed cache. And I can actually use that to cache a lot of database queries and also results of the API calls. Okay? So that somebody else, if they are asking for the same thing, they can very quickly serve from this Memcached instead of going to the database. Okay? So one common example I can give where you can relate that you are actually using Memcached. How many of you have done, let's say you try to buy a ticket, you're trying to do some search saying, okay, I want to go from place A to B, you see a very attractive price. Then you say, okay, let me buy. Okay, you continue, and then the next step you get a message saying, sorry, the price has changed. Has any of you seen that? No? So try that, okay? Many times you will see the price has changed. So what is happening here, that the first time you did the query, the results are coming from this Memcached. Okay, your query is actually not going to the database. So might be somebody else in your neighborhood or whatever the servers they are sharing, somebody did that search, and that price has come there and it's sitting in the cache, and then when you are asking the query, it is giving you from there. Okay? But when you try to really decide to buy that ticket, of course, the request has to go to the database to find out that the price is right and the seat is still available. Okay? And that is the time it actually gives you that message. Obviously, the question is, why are we then using Memcached? Okay? If this is not working correctly. It is working correctly, but if you see the behavior of a lot of us, we try to do a lot of browse, all right? How many times you search for airline ticket and then choose one, okay? So the same thing happens to the books. You might be searching for a lot of book and then take a decision. So they want to have a lot of these transactions where you are trying to do read only, okay? Trying to accelerate those based on the previous cache results of similar queries. Is that concept clear? Okay, so that's what happens. So they want to have these data centers because they are using a lot of this large set of clients. So they want to take the memory from each of the node and then combine. So this is how the distributed caching layer looks. Okay, and it's basically taking memory from each one of these. Then they have some key value stores happens there. Now, obviously, the first generation of things started with only memory. Now it is also being extended to SSDs. Okay, you can also do a 2-level designs where your primary is in the memory, the Memcached, but if that data space is over, then you also go to the SSD. So you can have some hybrid memory and SSDs design. So I will not focus on that. Let's just focus on the pure memory for the time being. Okay. So with this, now let's take a look at what is happening in the networking technologies and protocols. I showed this chart yesterday, just want to very quickly go over it, saying we know the clusters are becoming very popular, especially in the HPC world. And here we are seeing, like, not only InfiniBand, we have the 10 gigabit Ethernet or IOR, which is the RDMA being applied to the Ethernet, Internet Wire RDMA protocol, or this converged thing called ROCE, RDMA over Converged Enhanced Ethernet. So all these technologies are moving ahead very quickly. And we have seen that we are trying to get like the low latency, few microsecond, and also bandwidth 100 gigabits per second. And also because of this RDMA and offload, we get very low CPU overhead. Okay? And especially in the HPC area, many of us know like Open Fabric software stack has been accelerating the growth. A lot of different kinds of middlewares are being put together. And this is totally empowering a lot of these top 500 systems to come and use these advanced networking technologies. Now this chart shows from the top 500, if some of you have not seen this shows over the years how different kinds of networks are playing the role. So for any given year, it tries to find out from those 500 systems how many of are using networking technology JX versus Y versus G. Okay, and here these are different color coded. So broadly, this is the InfiniBand, this is the green, and then this is the Ethernet, and this is the new 10 gig which is coming here. Okay, these are others are proprietary and proprietary stuff. So as you might have seen that InfiniBand, when it started in the 2000, after some years 2003 onwards, it has started picking up, and now we see a lot of these the HPC clusters using InfiniBand. And in that context, we have seen like the most common is the MPI. I spent a lot of time yesterday and some other talks also trying to say most commonly used programming model, also parallel file systems, storage systems, almost 13 years or 13 and a half years if you take more precise thing has gone into trying to use the high performance networking technologies to accelerate all these programming models. MPI and then PGAS are coming. But at the same time, I mean, these are the numbers I showed very quickly, like we can get 1 microsecond latency, or if you use the InfiniBand, the dual port Connect IB, we get very close to 100 gigabits per second unidirectional bandwidth, and very close to 200 gigabits per second bidirectional bandwidth. But the question here is that most of the if you see the big data side, so this is the totally HPC side, so there is a different community, the big data, that's what we want to address here. They are still using Ethernet. Okay, and not only with Ethernet with sockets, so then they are able to run these experiments on a smaller scale system, but when they are going to larger one, they don't get the performance. So there are some limitations in the performance and scalability, but some organizations have started moving. Okay, if you think of like IBM or Oracle, in fact in their database environment, they have moved to InfiniBand already. Okay, so you see gradually those solutions are coming out, but in general the question is, what are the challenges in moving this kind of software or environments to a high performance network, and where the bottlenecks lie? Okay, so these are the questions in our group we started asking almost like 2.5 years back. Okay, because we were trying to do the MPI and PGAS stuff, and a lot of people were also asking like, why can't we take similar kind of designs? So we tried to ask 2 questions, and that's what I'll try to show the answers later on. So can these bottlenecks be alleviated with new designs which are similar to MPI? Again, you cannot just take plug and play. You cannot take the MPI design and then plug it there, okay? Because the environments are very different. That is one thing. And the second one is that can HPC clusters with high performance network be used for big data applications using Hadoop? So that means, let's say we have an environment HPC cluster here already, like let's say the Switzerland Center, or you take TAC or San Diego Supercomputer Center, or any organization, there are HPC clusters, they are using high performance file systems. So, and if somebody just wants to use MapReduce, not let's say HBase and all those things, can they still take advantage of this Lustre file system, but try to do big data processing in a much more efficiently? So we ask these 2 fundamental questions. Okay, so to answer that, we first try to see, okay, where these components lie to each other, and then what are the problems. So I showed a similar map yesterday for MPI and HPC programming model. So here also you can see like we have these commodity components here, multi-core, many-core, all different networking technologies are coming. And here the storage technologies also matter. Whether it is like hard disk or SSDs, those things matter. So again, I'll call this like a supply side. And then the top, we have the big data applications or benchmarks, and they are written with big data middleware. Okay, so this is where it sits. We'll see HDFS, MapReduce, HBase, and Memcached, these are sitting here, and they are mostly using this programming model, which is like sockets. Okay, so the question is like, if we want to really use these and need to accelerate, we have to put some kind of a communication and IO library here, okay, to bridge the gap. And this can have a lot of these components, like how do we again accelerate point-to-point communication. These environments use a lot of multi-threading, so we need to come up with some better threading models, synchronizations, enhancement to IO and file system, quality of service, virtualization, and fault tolerance. So these are like the broad topics. You need to carry out research to bridge the gap and deliver the performance from here to the top level. But to answer the first questions, instead of like going into each one of these, first we ask, because it is written with sockets, And this was exactly happening. Like if you, some of you remember, even when the InfiniBand started coming up, MPI was running over IP over IP. Okay, it was not running over VERS. It was not running over RDMA. Okay, at that time, like prior to InfiniBand, if some of you know, like Mirinet was there, Qualtrics were there, so they had done the high performance designs over those proprietary networks. But for InfiniBand, when it started coming, people were running IP over IP. In fact, there was a name called IB Nice. I don't know if any of you know that. That was the first term like Mellanox had in the beginning over IP IB Nice, run that, and then that was the MPI design. Okay, so same thing is happening here. That's what we saw, that people are running over sockets. So first thing we asked, that can we actually move to RDMA? That is the first question we asked. Okay. So to answer that questions, then you need to take a look at this open fabrics, how it is evolving. So the broad idea here is that, let's say you have an application or a middleware, there are two paths. Either you go through the sockets or you go through the verbs. Okay. So the difference here is that if it is written with sockets, your application or middleware, you are not changing it. But below, you are using, let's say, either some 1040 gig TOW, or you are using 1 or 1040 gig, or even using IP over IP. So you are trying to provide the sockets interface to that application or middleware. Okay. But on the other hand, like the very high performance MPI or PGAS, we are operating at this side. Okay. So that is where, instead of things being written with sockets, we actually modify it to run over verbs. That MPI is a middleware which has been modified to run over verbs. Same thing has happened with the PGAS. Let's say UPC, OpenSMEM, like I showed some examples yesterday, and today also we heard similar kind of thing. So that means once you modify your middlewares to the verbs, then your end applications can take advantage of it. Okay, so not that each and every applications you need to rewrite. Okay, so this is the same question we asked, saying that if we can move the Hadoop kind of a middleware to this side, then any big data application trying to use Hadoop can just run without modification and then try to get also the best performance. Is everybody okay with me? Okay. So that is the goal we try to ask here. So to abstract it up in a simpler manner, so you will see that this is what the current design, like people are using the big data applications over sockets. And then of course there are some different kinds of solutions from different organizations. They call like an accelerated sockets, but still they use like there are some kinds of an offload is used, but in this kind of solution also there is some kind of a mismatch, in the sense like the stream semantics of the sockets, there is an mismatch for the upper layers, like whether it is an Hadoop or Memcached. And of course, sometimes all these high performance networks have something called zero copy schemes. They are not available for non-blocking sockets, so you cannot take the maximum advantage here. So we want to ask this question, which is the right hand side, like taking, let's say, this RDMA or Rocky or InfiniBand, these are running with using verbs. So can we move the Hadoop big data design directly to the verbs? Okay, and that's what we'll see the solutions as we move forward. So I'll try to give, like again, solutions along two broad approaches I mentioned here. The first one is a pure Hadoop. So that means this is like whoever is using HDFS or MapReduce, RPC, HBase, they are in the Hadoop ecosystem, and we want to provide solutions to those people so that they can directly run over InfiniBand. That's the first thing. The second approach, as I said, people don't want to use a lot of these other components, but just MapReduce. Okay, and they also don't want to use HDFS. They want to use the existing Lustre or any other file system like GPFS or any other file system available with HPC. So the question is, can we also satisfy them? Okay, so we'll see both kinds of solution here. So what I'll try to do here, so the first, I'll cover the entire Hadoop ecosystem. So I'll try to go over some case studies and design how you want to redesign these components, starting from HDFS, MapReduce, HBase, RPC. And we'll see these designs and their benefits one at a time. Okay, just if we accelerate HDFS, what happens? Just if we accelerate MapReduce, what happens? And then I'll try to put them all together. Okay, and they can mix and match. So that means you can have an environment where only HDFS has been accelerated. You can still run everything else. Okay, or you can have only MapReduce accelerated and everything else is running over sockets. You can have those kind of hybrid solution, and I'll show the combination, and then I'll show some results of MapReduce, Hadoop MapReduce purely over Lustre, and then move to the Memcached. So not only like we started this research like 2.5 years back, but since last June, we have actually put together a lot of these components. Just like our MPI release, we have a release here, public release. So if any one of you are interested, you just go to this website, Hadoop RDMA to Ohio State, and you should be able to download this. So what we have done here, so this has like high performance design with native InfiniBand and also Rocky support. So you should be able to run it on either IB or Rocky. And this has the support at the verse levels for HDFS, MapReduce, and RPC. So those are the 3 components we have first pushed out. The HBase has not yet gone in. We'll try to add that in the near future. And at the same time, these are easily reconfigurable so that you can, with the same package, you can run over IB, you can run over Rocky, you can also run over the traditional sockets. Okay, so you maintain that API. So just by using different configuration parameters, you can do all these evaluations. Whatever numbers I'll be showing, you can produce it yourself and see whether that helps with your end big data applications or not. Okay, and in this, like in fact, just 2 days back, we did this release. The latest release is 0.9.9. So this is based on Apache Hadoop 1.2.1. If some of you are familiar, there's a Hadoop 1.2.1 series, like 1.2 series, then there's a new 2.0 series. So we have not moved to the 2.0. We'll be trying to do that in the next 4 to 6 months. We'll try to move there. And this is compliant with the 1.2.1 APIs and applications. So that means if you have some other middleware, some other applications using a Hadoop 1.2.1, you should be able to directly use it. There are no changes. You don't have to touch your end applications. So think of it as like just like MPI, we talked about a lot, MPI 1, MPI 2, MPI 3. So for example, if it is an MPI 2, your job is of MPI 2, you just use the middleware to run your MPI 2 jobs. So similarly in the Hadoop, there are different releases, different series, and they have different architecture. So we are trying to make it compatible with those standards. Okay. And of course, we have tested it on all different kind of IB adapters, Rocky, various multi-core platforms, different file systems, and disks and SSDs. So let's see how we have gone ahead with this kind of designs. So first, we'll try to take the HDFS. So the HDFS, if you see, as I said, there is a replication process. So that means we are trying to write the data, and when trying to write the data, it actually replicates. And this is where the most of the time goes. Okay, so we first try to accelerate that. And instead of like trying to do the sockets based replication, here we are trying to do RDMA based replication. And then there are also 2 kinds of models. One is a pipelined replication, because as I said, like HDFS has like 3 copies, so the default is pipelined. So that means first it copies to some node, that node sends to other one, that node sends to another one, and you get an acknowledgement back. Okay, and the other one is parallel replication, so where you can directly from the same node you write to 1, 2, 3. Okay, and I'll show this difference between the pipeline and parallel a little bit later on. And so what we did is like this is where it is written with the Java native interface JNI, and we try to breeze that to the directly verse layer. So our design is actually sitting here. Okay, and of course it has other kinds of like, let's say the HDFS read, which is mostly local. So we don't have to optimize that because it is happening over the node. And there are also some other RPC components and all, which we'll talk about later. So what we did is like gradually started identifying what is the critical communication path and where the most of the time is going, and to start moving it to the verse. Okay, and all other parts still remained over sockets. Okay, and then we try to gradually move from one design to the other. So this is the paper, actually the whole paper we presented at SC12. You can download and take a look at it. So here these are some results. So what we are trying to do here like is the same set of nodes we have in my lab. We have 10 gigis connected here, so these are the 10 gig Chelsea cards, and these are the IB QDR, but they are running with 2 different protocols. So this is the IP over IB. So the standard HDFS and Hadoop, as I said, can run over, because they are written with sockets, they can written with IP over IB without any issue. And then this red line is actually our RDMA based or verse based design. Okay, so we are comparing on the same hardware, two different networking technologies, Ethernet and IB. And for IB, we have the standard default and the enhanced design. So now we can see here, and this is like the different file sizes we are seeing. This is just the communication time. We are just trying to look at like a micro benchmark evaluation here. And here we see like almost for a 10 gigabytes data, the new verse-based design can improve communication time by around 30% and around 56% compared to 10 gig. Okay? And so then we tried to run, these are the low level things, then we went a little bit up. Typically in this HDFS, there is a common benchmark called DFS-IO. Okay, so that is a common benchmark which is used, and that is like a MapReduce based application. So what we are trying to do here is the thing, the DFS-IO is actually running with sockets. Okay, so we have not changed that. Later on I'll show you the combined number. Okay, so the DFS-IO is running with Ethernet, but the underlying HDFS is running over the bus. And we have again similar kind of designs here. And what we see here, like these are the hard disks, these are the nodes connected with hard disk, and these are the nodes connected with SSDs. Okay, and what we saw here, like let's say you take around 20 gigabytes of file size compared to IP over IB, we see around 24% improvement. And on this side, if the nodes are SSDs, the improvement is very significant. We see around 61%. Okay, so first we were a little bit puzzled. What is happening? Okay, and once we understood what was happening, the idea here is that let's say on this kind of system, your hard disk is the bottleneck. So even though we change our communication protocol or the networking protocol, we still don't get a lot of benefits. On the other hand, you know, compared to hard disk, the SSDs have much more better performance. So that means we are alleviating that bottleneck, and now the high performance network is giving more benefit. Okay, even prior to us publishing, there are some publications in the literature where you will see that people have claimed saying no, high performance networks will not give you much benefit for HDFS and other big data applications. So what was happening is they were on this side. Okay, but as soon as you move to SSDs, or if you have multiple disks and all, I'll show you in the next few slides, you will really see the benefits of high performance networking. Okay, and I give this example, you might have heard again from some talks. If you have a very old car, okay, and you want to run it faster, if you just go and try to change the tire, it will not run faster. Okay, engine might be your bottleneck. So you change the engine, you change the transmission, and then put a new tires, you will see it will run faster. That's what is happening here. So you need to take a balanced approach in your system, saying where is the bottleneck. If your hard disk is the bottleneck, your storage is the bottleneck, then no matter whatever you do with your high performance networking, you will not see the benefit. Okay. So then we tried to do this study. So here what we are trying to show, the same cluster, again we have 10 gig IP over IB and the new design, but we are trying to have one hard disk and two hard disks. Okay, for each one of these, 1, 2, here again 1, 2 with IP over IB, 1 and 2. So here we'll see that, of course, with one hard disk, we get around 24% improvement, but now if you have two hard disks, you will see 31% improvement. Okay, because the data is being replicated to different disks, so they're operating in parallel, so we are alleviating the bottleneck, and now the high performance network is helping. And two hard disks versus one hard disk, so this is how we see around 76% improvement here, and then 66% improvement for IP over IB. So those are like the small scale studies. Then we try to see that can our design scale to a larger system. So here we try to run these experiments on the San Diego Supercomputer Center. Some of you might have heard of a system called Gordon. So they have actually, it is a data intensive cluster, and each one of their node has a SSD. Okay, this is a very unique architecture for data intensive workload. So here we had like 32 data nodes, and each one has 16 cores. So we are effectively running a 512 core job here, and if you see for different file system size, so this is the aggregate throughput and then the execution time. So we see here around 47% improvement in throughput and 16% improvement in latency. Okay, and as you know, a lot of these big data applications are actually throughput oriented. So that's what we are trying to see, more benefits in the throughput. So then similar kind of things we try to do it on the TAG Stampede, that is the Texas Advanced Computing Center, the Stampede system. Here we try to run up to 1,000 cores, 64 data nodes, each one has 16 cores, and they have one on hard disks. And that size is also smaller. So we took two extremes, one with SSDs and one with hard disk. So here again we see like the throughput we can get, this is also has FDR. That has the QDR, the SDSC. So here we see around 64% improvement in throughput and around 37% improvement in latency. Okay? So that means we are able to scale to a larger system. Any questions so far on the HDFS? Okay. So now let's move to the next component, so the MapReduce. So the MapReduce, again, similar kind of things we wanted to do, like taking when the MapReduce earlier I had shown, like the shuffle stage, which is happening over the network, that's what we want to optimize. So here again, we try to move directly over to the verse. But at the same time, because the MapReduce, the mappers have results in the memory, and the reducers are also taking the things into the memory, you can do a lot of additional optimizations. So here we have like some free fetching, caching of map outputs, in-memory merge, and then the question is how you actually overlap. So like there are three phases happening, mapping, shuffling, and merge, or you can also overlap with shuffle, merge, and reduce. So all this kind of overlap, we try to orchestrate well so that you can get the best performance out. And here again, like the other paths still remain with the sockets to provide compatibility. So these are the numbers. So this we presented last year at the IPDPS conference. There was a workshop, HPDIC workshop. So what we are trying to show here, again, these are some results with nodes with hard disks, and these are with SSDs. So what we are comparing here, again, they have 10 gig, and then this is the IP over IB. Then this is a solution UDA. Mellanox has this solution, so we are trying to compare with that. And then this is our solution. And this is across different data size. So here we see like we get around like this is the QDR system, so we get around 41% improvement over IP over IB. And also compared to UDA, we get around 39% improvement. And the right hand side, these are with SSD, so we see some better numbers here, around 52% improvement over IP over IB, and around 44% better than the UDA. So then, those are the low level numbers. Then we wanted to go into TeraShort. So that is again another benchmark a lot of people run. So here what we are showing, like this is again 8 data nodes with 2 hard disks per node, and this is for different data sizes like 60 gigabytes, 80 gigabytes, and 100 gigabytes. And we also see similar trends like 51% improvement over IP over IB and 41% improvement over UDA. And then we moved into a little bit larger cluster to analyze the scalability. And so so here again, just like HPC, you also need to think of like whether it is a strong scaling or weak scaling. Okay, there are 2 kinds of applications, whether you keep the data the same and then try to keep on using more and more number of nodes or cores, or keep the amount of data per node and core constant and then you keep on increasing. The same ideas apply from HPC side. So here what we try to do is like this is trying to show like 60 node with 60 gigabytes to 64 with 240 gigabytes. We went, and then here we see like around 240 gigabytes, we see around 40% improvement, okay, compared to the IP over IB. And here this is on the TAG Stampede. Again, we went up to 64 nodes, which is 1,000 cores, and for 320 gigabytes of TeraShort, I think this is TeraShort, yes. So we see around 38% improvement. Okay. So you see this consistent story as we go over the slides. You will see that not only like just by changing from like using the RDMA based design, you are able to improve compared to the IP over IB. Okay, because sockets level you are not able to optimize, and then better designs you get better performance here. And then there is a different workload here. This is called PUMA. This has been published by Purdue University, so they have a workload here, so we try to take it. So they have different kinds of things: adjacent list, self join, sequence count, word count, invert index, etc. And so here what we are trying to do is the 10 gig numbers we are trying to normalize with that, because each one had different computation time. Okay, so you can think of like this is like the in the HPC side we have NAS parallel benchmarks. A lot of people use. So similar kind of benchmarks are coming out in the big data world. So this is one of them. There is another big data bench. A lot of people are working in similar areas, and it depends. Each of these benchmarks have different kinds of computations to communication ratios, and wherever you see more communication, you will see more benefit. That is expected. And so here we see like a self join or sequence count. We see a lot of improvements, like around almost 50% improvement compared to the IP over IB. So then there is another workload here from Swim. It's called Swim. This is actually from Facebook. So Facebook people have taken some of their internal jobs and then trying to create a synthetic workload out of it. Okay, so it's not the actual Facebook workload. They cannot put it outside, but it reflects their job. So a lot of small MapReduce jobs are executed here, and here we see like, so there is this is the IP over IB, which is the upper line, and then the RDMA based design. So here we see around like 24% maximum benefits and 13% average benefits across all these 50 jobs. So then let's move to the HBase, which is the other component. So here what we try to do, we try to analyze a little bit more details where the communication is going or where the time is being spent. So for each one of these here, we'll see like this is an HBase put, this is HBase get, this is IP over IB, this is 10 gigi, this is the RDMA based design. We try to go inside and try to seeing how much time is being spent in communication preparation, server processing, server serialization, client processing, client serialization, etc. And we see that, of course, most of the time is going in this communication and communication preparation. Okay, so here you will see that this is the IP over IB, it takes a lot of time, 10 gig is reduced, and then the RDMA design significantly you can reduce. Okay, and so here we see like for HBase 1 kilobyte put or 1 kilobyte get, you get almost like a factor of 6 improvement compared to 10 gigi. And then here there are different kinds of micro benchmarks for the HBase. So one of these like a single server, multiple clients, and this is trying to show in terms of latency as the number of clients are increasing. And here the same thing is throughput, operations per second. And here we see around like 27% improvement in the throughput for 16 clients over 10 gigi. Then this is another YCSB workload. So this has been provided by Yahoo. It's called Yahoo Cloud Service Benchmark. So here it is showing like a read latency and write latency. Here again up to 128 clients we try to evaluate, and we see around like 40% improvement in this benchmark. And so then there is this RPC. As I mentioned, like this is the remote procedure call, which is extensively used in the Hadoop environment for exchanging control information, trying to find out heartbeat, monitoring. So a lot of communication goes over that, so we try to accelerate that. Okay, and if we can accelerate that, it can benefit all the other components. And so similar kind of things. So here what we did, RDMA or send receive based adaptive communication, some good buffer allocation, on-demand connection setup. And here we see like this is trying to show like different kinds of payload size and then the latency. And here we get almost like this is the 10 gigi and IP over IB, and this is the RDMA based design. So we almost get 60% improvements, just the basic RPC latency. And in terms of throughput, here you can see that this is the new RDMA based design goes into almost like 100% improvement compared to the other solution. So then let's try to put it together. So these are, I showed all individual numbers, and these are the things compared to the latest release what we have done. So if you download, you will see, you should be able to see exactly similar performance. So what we have done is different kinds of test beds, different kinds of benchmarks, and then I'll show later on like the benefits of parallel versus pipeline replication. So here, so this is like the same HDFS IO, but now using SSDs. And here we see these are the left hand side is like latency, the right hand side is throughput. So here we get around almost like 13% improvement over IP over IB. For 5 gigabytes, for 20 gigabytes, we get around 30% improvement for 10 gig. And for the throughput, these are like, it varies for different data sizes. We get around 43% to 64% improvement. So this is the large scale experiments. So this is on the TAC Stampede, 32 nodes, like 512 cores, and we use a total of 128 maps. So there also it depends like in the how many mappers you are running, how many reducers are running. So we are just trying to show some sample numbers. You can find out for your application which combination works out to the best. This just like HPC, we have like MPI plus OpenMPI. How many MPI processes you run, how many threads per process you run. The same kind of things are also similar kind of things happen here. And here we are trying to show like we get around 36 to 38% improvement in the latency and around 60% improvement in the throughput. And so this is the random writer and sort. So in the random writer, this was run over the SDSC Garden. I talked about like using SSDs. So we get around like 16 to 20% improvement here running a random writer for 300 gigabytes of data. And when you do a sort on that 300 gigabytes of data, you get around 36% improvement. Then these are the numbers on TAC Stampede. So here we are trying to show TeraGen and TeraSort. This is the other benchmark. This has the hard disk as I indicated earlier. So these numbers are with 64 maps and 32 reducers. So the benefits come here in the TeraGen part around 17%. Here it is around 38% improvement. So as I indicated earlier, the default Hadoop actually, or the HDFS does pipeline replication. In the latest release, we actually push the parallel replication, okay? And so here what we are trying to show, the earlier numbers like this is 10 gig, this is the IP over IB, this is the pipeline, and this is the parallel. Of course, this parallel is only a degree of 3. I mean, if it is a more number of replication, you will see more benefits. But just even in the degree of 3 replication, we are trying to get additional squeeze out another like 10 to 12% performance benefit here by just changing from pipeline to parallel. This is over 8 nodes. Any questions in this part? So now let me move to the next one, which is the Hadoop. People want to use just the MapReduce. Okay, forget about all HDFS on HPC cluster. So if you have an HPC cluster with Lustre, people want to use just the MapReduce. And we saw that a lot of people are just using the standard IP over IB. Okay, in fact, a lot of solutions from the vendors, if you talk about Intel or Cray and all, that's what they run. Okay, so we tried to see whether our RDMA based design can work there. Just the RDMA with the MapReduce, anything else. So this was the very first initial study we have done. So this has run over TAC Stampede. So this is like on 64 node 1000 cores. You see, just by using the RDMA based MapReduce, you can gain almost like a 44% improvement for 500 gigabytes of sort. And here is the HDSC Garden for 100 gigabyte sort. You get around 33% improvement. Okay, so these are very fresh numbers. Just last few months we have worked on, but there is a lot of things can be done by taking the Lustre, their features and all. So instead of using HDFS, now if you use the Lustre, we can still enhance the MapReduce more stronger. So in the next few months, you will see some better results coming out along this direction. So now let me just try to move ahead. The Memcached, as I said, this is for the distributed caching layer. So here the designs what we have done, that because it's like a client server, the multi-tier data centers. So we have tried to, the design has something called a sockets worker thread and burst worker thread. So that means if the client is coming with the sockets, they can work with the sockets worker thread. If the RDMA client comes, it can work with the burst worker thread. And here we see like the Memcached, basically as I said, it's a key value pair. So you operate on get and put. So here it is a get latency. What we are trying to show is IP over IB 10 gig. And here actually this was a little bit older study. That time the DDR, the cluster had DDR. So we are trying to show 2 solutions, and that's also using RC and UD, 2 different protocols. So here we see around factor of 4 improvement compared to 10 gig. And in the Memcached environment, also transactions per second matters. Like as I said, the example, like the buying the tickets and all, how many customers you are able to handle, not just the latency. So here we are showing like compared to like IP over IB, the RDMA based design significantly goes up. And this is for large number of clients. We went up to 1,000 clients, and you see a peak here, and that depends on the architecture. Like that time, we had 8 cores per node. So that means up to 8 clients, they are coming, so you are able to handle it within the node, not going outside. So that's why we see a peak. And now the newer modern multi-cores are coming, 16, 24, 32, so you will see a peak like that and then come. Okay? But still you will see, compared to IP over IP, here we are getting a significant improvement in the RDMA design. So then recently we tried to run it over TAG, just to TAG Stampede to scale it up. So this is a number like of different message sizes, the gate latency, see the benefit. We are almost like up to 1,000, here we went up to 4K clients. We can reduce the latency by a factor of 20, okay? Because we are able to aggregate very large memory across 4,000 nodes. So this is a very big distributed caching layer. And then using RDMA, we are able to significantly reduce the latency, and the throughput we are able to push by a factor of 2. The overall transactions per second happening here. And then this is another kind of a benchmark which gets used in this environment called Olio. The similar trend we see around like factor of 4 improvements. And then this is a workload. I have one of my earlier students working at Yahoo. So we worked with him to take their Yahoo, the marketing benchmark, like whatever they sell it to their advertisers and all, taking that kind of a benchmark, and he gave us a application workload, and here we see like compared to the IP over IP, we get around almost 12 times improvement for the IP over IP. Okay, so these are the kind of like Memcached. Again, we have not made the release. We want to plan it to do it again in the near future. So as of now, you get the Hadoop with the HDFS, RPC, and the MapReduce. Okay. So let me then wind up with saying what are the remaining challenges here. If we take a broader picture, if you remember, I introduced this picture. What we have just done is just touch 2 of these points. Just the point-to-point communication and some I/O file system issues, and we have moved this to the RDMA protocol. But the question here, as we have started looking, there is a lot of opportunity to optimize this middleware. These middlewares are written with slower network in mind, okay, or with sockets which have higher overhead in mind. But now, since we have accelerated that, we can reflect back saying all these data structures inside or the protocols, they need to be enhanced, so then we can get even higher benefits. So that is in our next phase we are trying to do. And then these are some of the like the very broad challenges I talked about, like multi-threading synchronization, QoS and virtualization, support for accelerators. I think Axel mentioned even that area is coming, like how do you take big data together with accelerators, fault tolerance enhancements, and especially the support of parallel file system like Lustre. I just showed some initial numbers, but there's a lot of opportunity to do. But at the same time, when we started looking at it, there is a bigger thing which is lacking in this community is the benchmarks. Okay? And so the question here we tried to see that the current benchmark sufficient. When I showed the numbers like sort, Terragen, these are the upper level workload people are trying to use. But the question is like, what is happening at the lower layer? Where the benefits are coming? Which design is leading to benefits, or which is not getting benefits? There are no insights. Okay, and so if you see here, so what is happening is all the benchmarks are here, and there are no benchmarks here at all. So when you try to work out some designs, you don't get any insight saying, am I losing, am I gaining? Okay, and also there is no correlation here. And obviously this is nothing new to us. When we started this MPI project in 2001, the same exact issues we encountered. Okay, and in fact as a byproduct, we introduced these OSU micro benchmarks. Many of you might be familiar. This comes as a part of our MapReduce releases. And over the years, we started with MPI 1. It has been extended to MPI 2, collectives, GPU aware, OpenSMEM. Even in the GPU aware thing, you see a lot of these legends these days, H2H, H2D, D2H, all those things we introduced. And a lot of people have been extensively using those benchmarks. In fact, now this OMB has become actually a part of a lot of procurement. You see the procurement documents, they are saying, okay, report the numbers with OSU micro benchmarks. And that's what actually we want to do here. Okay? So we want to introduce a lot of micro benchmarks for this Hadoop design or the big data design so that people can actually use those to compare and contrast different solutions and saying for different platforms or different networks, different computing platforms, they want to see this. So So looking forward, these are our future plans. As I said, we just made a new release. So those of you who are really working in this area, please feel free to download that, try it out, let us know. We'll try to push the HBase as our next things, and then we'll be moving to Hadoop 2.x. And then in the pipeline, we have the Memcached RDMA coming. And then, of course, research side, we need to explore all these things, and then going into these advanced designs with the upper level optimizations. Okay, so that will take us some time to really understand the interplay, and then also introducing the comprehensive set of benchmarks. So with this, let me conclude here. Broadly, what I did is introduced you to these big data things. I discussed some of the challenges and went through some of the case studies, and these results are promising. But once again, this is just a new area. I mean, if you think MPI and PGAS, 14 years of R&D has gone, here only 2 years. So a lot of issues are similar, but it will also require a lot of effort and time to come with the complete solution, and that's what we'll be trying to do in the future. And then once again, just like yesterday, I want to acknowledge all my past and current students. These are some of the pointers. Okay. So thank you. If there are any quick questions, I can answer. Otherwise, we can talk offline. Any questions?
Okay.
I thought big data will have big questions. Okay. Thank you.
Thanks, DK.